we can quickly get started with the session. And I'm sure that everyone, they already finished the keynote now, and I'm sure that people will start joining the parallel sessions now. So I would like first to introduce Professor Abel Olorunnisola. He is a professor at the University of Ibadan in Nigeria. He was supposedly the session chair for session A6, but due to some other commitments, he will only do his presentation and he will have to leave. And I will handle the session with Lubna. I would like to invite Professor Abel to start his presentation. Dr. Abel, the stage is yours.
Thank you. Thank you very much. I need to share my screen.
Mm-hmm.
Okay. Sorry. I'm sorry, just 1 minute.
Yes, take your time. If you need any help, just let me know.
Okay. Yes.
I can share the screen from my side if you wish.
Okay. See my screens, please.
Okay, can you share again? I accidentally stopped it. Sorry.
Okay.
Can you try to reshare again?
Okay.
Yes, perfect. Just go to full screen mode.
Okay.
Mode.
Okay. Well, it's still morning here in Nigeria, so I say good morning. Even though I think it's about evening there in Malaysia. So wherever you are hearing me, I say greetings from Nigeria, where I'm speaking from, and I'm in the western part of Nigeria. And my university is University of Ibadan, Nigeria. So I also bring you greetings from my university. Now, this presentation was prepared by two of us, Ogudipe, not presently available, so I'm presenting on behalf of the two of us. And the title of the presentation, as you can see, is Effects of Partial Replacement of Cement with Selected Polymers on Sorption and Mechanical Properties of rattan fibre-reinforced composite roofing tiles. Now, asbestos cement has been a popular roofing and ceiling material for many years, but because of the health issues associated with handling of asbestos, many countries have banned asbestos, even though it's yet to be banned in Nigeria, but gradually it's going to happen. And there's a need to proactively prepare for a time like that. So in the last 40 years, many people have worked on the use of natural fibers as replacement for asbestos, because asbestos itself is a fiber, and it's just a fiber mixed with cement. So people have used different kinds of natural fibers to produce roofing sheets, ceiling boards, and other building materials. There are too many of them to mention. So just to note that sisal fiber has been used, banana fibers have been used, flax fibers have been used, and many other fibers. But we have tried to look at the use of a palm product, rattan, and its fiber as a replacement for asbestos in many parts of Africa and Asia where rattan cane abounds. Because even though rattan is well known as a furniture material, there's a lot of wastage involved in the use of rattan for furniture production. Many times, if it does not look nice, that is not fit for furniture making. But actually, the rattan cane that doesn't look nice enough for furniture making can be converted into fibers, processed to fibers, and mixed with cement for rattan cement fibre-reinforced materials. Now, we have used rattan particles in the past. In my research team, we have even used rattan cane furniture waste. But we move on to converting the rattan to fibers and mixing with cement and looking at their behavior. Challenge with using cement for production of building products. For example, there is a challenge of CO2 emission in the manufacture of cement itself. And so environmentalists are opposed to the level of CO2 emission in cement manufacture. There's also the challenge of rising costs, including Nigeria. So the solutions is to try to partially replace cement with some other materials. Now, the usual trend is to use pozzolans, things like rice husk ash or any of the wood ashes that have pozzolanic properties, so that you can minimize the quantity of cement that you need for production. But it's also polymers with cement. And so we have tried here to see how the product will behave if you partially replace cement with two natural polymer sources and then one synthetic polymer. So the primary objective was to investigate the effect of rattan cane fiber reinforced roofing types and the specific
Dr. Adam,
case species that we used was like this.
Professor
Can you hear
Adam,
me?
just to interrupt, I think your connection is not stable. Can you please switch off your camera? Perhaps this will save the bandwidth.
I should switch off my camera.
That's perfect.
Okay. So can you hear me now?
Yes.
Okay, thank you. So sorry about that. I've been having challenges with connection here. So sorry. So we have worked on Laccosperma secundiflorum, one of in Nigeria. And so what we had to do was to collect the rattan canes, which you can see on the left-hand side of the screen. And then we processed into particles by hammer milling. And then we digested with sodium hydroxide, 10% weight per volume at 100 degrees Celsius at the pressure of 1 atmosphere for 2 hours. This was based on previous studies that we have conducted on producing rattan fibers, and the best yield was obtained at this level. And so the fibers obtained were thoroughly washed and then dried in accordance with standard practice. And so we also use 3 polymeric materials. These are natural rubber latex, a climb by known as Cissus populnea was also obtained from a plant. And then we used acrylic emulsion latex, which is a synthetic paint. So we collected all these materials and processed them appropriately. I don't want to bore you with the processing methods, but the details will be available in the full paper. Now, that is a photograph of Cissus as it was when it was in billet form, and then when the gum was extracted. The gum that was extracted and used is on the right-hand side of the screen. Again, these are details of fresh limestone Portland cement. That is the available cement type in Nigeria. In the past, Nigeria used to have ordinary Portland cement, but what we have now is limestone Portland cement, and that was what was used in this study. So the roofing ties were manufactured with 3% rattan-fibre content, and cement was partially replaced with natural rubber at 5, 7.5, and 10%. By weight, by rubber latex, acrylic emulsion at 10 to 20 and 30% by weight of cement. Now, these were also based on preliminary studies that we have conducted in this area. We have actually previously published some studies in this area. And so those ratios were based on our preliminary findings. And we used the ionized water for the production at 0.5%, 0.5 cement water ratio. And we also vibrated the products that were obtained at 50 Hertz for 60 seconds, also based on preliminary studies. And these are samples of the boards that were produced. Now, we prepared the materials, conditioned them, and we tested 5 samples after 28 days of curing. And the specific properties that we determined include density, water absorption, thickness, swelling, apparent porosity, rupture, in accordance with international standard, Indian standard 14862 that was published in year 2000. Now, these are some of the results that we obtained. Actually, we did more than what is reported here. For example, we determined the thermal conductivity, we determined the impact strength, but those ones are not presented here. Hopefully, most likely, those will be presented in the full paper. But looking at the density of the products, the control sample gave us a density of 1.23 gram per cubic centimeters. And the moisture content was also determined at 11.9%. And we can see that as we added acrylic emulsion and natural rubber latex, they reduced the density. But Cissus populnea gave us a density close to that of the control, while for the other ones, the densities were Cissus populnea, because in all our findings, we found out that it played a prominent role. That at the different ratios, 10 to 30% of the compound
Dr. Abel,
cubic centimeters, because usually it's preferably above 1 in the strength. So hello, can you hear me?
yes, just breaking a little bit, but now we can hear you.
Oh, okay, thank you. So I will see that densities compare favorably with other boards that we have produced from Rattan. Natural rubber latex reduced the density significantly below the level that is actually acceptable. But natural rubber latex gave a density that is within the range that is acceptable. So within 24 hours. The values obtained ranged between 0.62 and 1.66. Now, for all the composite samples, the samples that had polymer content had higher water absorption. And we can see that in this table. You can see that the water absorption for all the ones that contain the composites had a high water absorption. That was expected because these were hygroscopic materials that had affinity for water. But again, you don't want your composite to absorb too much moisture, because there are 2 different things that can happen. One, it will increase the weight, and then in increasing the weight, it creates a problem if it is on a roof. 2, the water retained can have effect on the vegetable material that is inside. It can lead to decomposition. So that's why you also don't want your water absorption to be too high. Now, usually when a composite absorbs moisture, there's a tendency for it to swelling. So we measure the thicknesses at different sides of the composite. And usually you don't want your thickness swelling to be more than about 2 to 3%. So we can see that for all the composites, the thickness swelling was acceptable. But again, the Cissus populnea gel gave us a thickness swelling that yeah, is higher than some, and the water absorption is also higher. And but all the thickness swelling values were below 2%. For example, for natural rubber latex, for the samples containing 7.5% and 10, the thickness swelling was above 2%, which is acceptable. Acrylic emulsion gives us a lower water absorption. And we found a direct positive correlation between water absorption and the thickness swelling, meaning that the more the water that was absorbed, the higher the thickness swelling. That is shown in that figure that we are looking at. Now, we also looked at how porous the materials were. We found out again that for the Polymer-cement admixtures, the apparent porosity was higher. That was expected because they have lower density. Adding the polymers to them reduce the density. And once you have a lower density, of course, it means that the material is more porous. But we can see incidentally for the samples containing Cissus populnea, the porosity was lower than for all the other samples, even including the control. Now, there's a need to investigate this further, and we are carrying out further studies on this, looking at the microstructural images and to see what exactly happened at this stage. Unfortunately, as at the time that we prepared this, we had issues with the scanning electron micrograph, so microscope, so we couldn't do that. But it's already ongoing to see what exactly contributed to the behavior of the Cissus populnea gel. But we can see that the porosity of the materials produced than all the other samples, including the control. Now, in terms of the stiffness of the material as measured by modulus of elasticity and the bending strength as measured by modulus of rupture, we can see that the values were quite low. For MOE, the values were, as you can see, for all the samples except the ones containing Cissus populnea, they were less than 3,000. Usually for most composites, you want the MOE to be at least 3,000 newtons per millimeter squared. It was only the samples containing Cissus populnea that gave us something above 3,000. Again, suggesting to us that Cissus populnea added to the stiffness of the products. Now, if you also look at the modulus of rupture, usually depending on the application, some standards will say anything about 4 to 4.5 newtons per millimeter square is okay. Some will say 9 newtons per millimeter square is okay. But all of them, the values we obtained were lower than 9 newtons per millimeter squared. But the samples containing Cissus populnea gel had
Dr. Abel, okay. I think Professor Abel was disconnected. So, Lovna, can you hear me? Okay.
Yes.
Okay, so we're sorry about the technical difficulty. So